Hello, we're doing linear programming formulation of game theory, which is mainly designed for Edexcel D2, but it may be useful elsewhere on other courses and other modules or whatever. We have a matrix here, which is a payoff matrix, and each of these gives a value of the gain for these various options. So, for example, this option here is -2. That means if Laura plays 1 and S plays 2, then Laura wins. Laura loses 2 because it's -2, and S gains 2 because of the -2. Right, so we need to define let's talk about decision variables first of all. Well, let's add 6 to each module, and the reason why we do that is we cannot have negatives. So we end up with, comes to 4, 14, 5, 13, 10, 3, 7, 1, and 10. Okay, so that's our new matrix. But we can't just do that without defining what we've done. So what we say is let V equal to value of the game plus 6. So that's important for our thing. Now, of course, we're doing it from Laura's point of view here. So we are looking at what Laura needs to do here. So we're saying that we'll let P1 be the probability that Laura plays 1. Laura plays 1. Let's say row 1. And P2, let's move that across so I can put. So we can say P2 be probability Laura plays row 2. And P3 is a probability that Laura plays row 3. Okay, so that's the decision variable sorted. Now, the objective function is maximize, and we need to make into a function P equals V. Now, some people think that's a bit strange. It's like, how have we introduced this other thing called P and make it equal to V? That's just simply because we need to make an equation of it. Probably the best way to remember that is when you're actually doing the solving using a kind of rugby post method for, obviously we're not doing this here, but imagine you were in another situation doing a rugby post method, say, something like that. What you're actually doing when you're finding that maximum point is you can think of this as going, let's put my feasible region here. And we can think of that maximum point there. It's not a very good diagram really, but never mind. Or optimum point is basically the highest point. Let's do that. Is the highest point that this objective line actually makes, and we can give that objective line the equation P equals to V. So it's a good way to actually think of this. It is actually connected. But basically what we're doing when we're doing game theory using this kind of rugby toast thing is we're actually effectively having a horizontal objective line which we move upwards to find the optimum point. Okay, just thought that might be a useful way of remembering it, and it actually is connected there. So let's maximise P equals to V. Now, we need to have constraints. Subject to right, now we've got, if we look at the numbers in our cell now, we've got V. Okay, V is less than or equal to 4P1 plus 13P2 plus 7P3. Okay, again, going back to the rugby post, if you want to think of a way of remembering which way the inequality goes, notice if you were doing this and you were writing these as inequalities here on the rugby post method thing, that all of these are, the V is going in that direction, the inequality. So use the rugby post, think the way you set that up to make sure you know which way the inequality is going in this case, because it's kind of, it feels a bit strange really, because in fact, of course, V would be equal to these. When we're actually setting it up, that often we could think of them, we might intuitively think them as equalities or equations, but what we're actually doing is formulating it as a linear programming problem, and that requires inequalities and slack variables and all the rest of it when we put it into a tableau. So this is what we want. And the actual question in this case, it says writing the constraints of inequality as inequality, so it's pretty clear. If you write an equation for it with an equality sign, then you're going to be penalised. You probably would normally be okay writing equals here if it hadn't said write in them as inequalities. Okay, we've got also the one to do with the probabilities, because these probabilities must all add up to 1. Yeah, they should all add up to 1. But again, we need these as inequalities, so what we say is that they are less than or equal to 1, which is also true. Obviously can't be more than 1. So less than or equal to 1. Don't forget the non-negativity constraint. That's very important. Can be equal to 0, and you've got to make it a non-strict inequality there as well. So that's basically the structure of it. It's not, you just need to learn it really. Let's say in terms of remembering the direction of the inequalities and the P equals to V, think of your game theory, and let's just do it there, and that should help remember which way the inequalities go, because you can think of this here as being our feasible region. So think of the area below as your feasible region with your rugby post kind of thing with game theory, and then that should help you, I hope, to write up your linear programming formulation for game theory. Okay, not a lot. I think that question was from 2008, I believe. I could be wrong, but I think that's summer 2008. It comes up every now and again, this. As of 2006, hasn't come up for a little while, so sort of 2016, give me like 10 years there. It hasn't come up for a while, so maybe we're due one. The next one is from 2005. It really isn't much different to what has been said before, but let me just tidy this up so I've got a bit more room first. Yeah, so the thing that's different here really is that it wants it from the other player's point of view, and we're used to this in game theory. If we're looking from it from the other player's point of view, we need to transpose the matrix first. That means change your signs and kind of move change your signs and move that row there would become a column. So that means -6, 2, 3. that row becomes the next column. So that's 3 minus 1 minus 2. And this row becomes a column. So that makes it minus 5, minus 4, and 1. Okay, and then, so again, we need to make it positive. So we're looking for, and not 0 as well. So this time we're adding 7 because the smallest number is minus 6. So we're going to get 1, 10, 12, and then 9, 6, 3, 10, 5, and 8. Okay, and then the rest is just the same. So I'll just write that up now, and just to save a bit of time, because there's another question with a little bit of different aspect to it. But basically now it's just the same with different numbers, and we've got no problem with that. We have to just say let v is equal to value of gain plus 6 and so on. But I'll just write that up now quickly before we do the next question. At this point you might want to pause the video and see if you can actually write up the constraints, the decision variables constraints and objective function, but it will be much the same as before but with different numbers. So if you want to try and do that now, pause the tape and the answer will appear in a second. So there we have it. Notice, of course, the only difference here is obviously we've got R along the rows now. So we've got it from R's point of view, but that's what it said. It's inequalities again, so we needed inequalities.